Thanks for inviting me. And the two topics I will combine in my talk is climate sciences, or very large scale climate simulations, high resolution climate simulations, and artificial intelligence. So now the question may be, how do they fit together? Well, they fit together in that many of the systems that we are running today have been defined to run artificial intelligence workloads. So all these GPUs and accelerators like tensor units and all kinds of things like this. And now climate simulations will need to take advantage of this in order to perform well in the future, such that we can predict localized extreme events such as droughts or hurricanes or floods and things like this. Absolutely. That's a great question. On the climate side, I started about 10 years ago, I would say, when I arrived in Switzerland. And the background there is that a bunch of colleagues, professors at the university, were asking me to join a project on kilometer scale climate simulation. So here the idea is that we want to simulate the whole Earth at about a 1 or maybe 2 kilometer resolution. And as you probably know, the Earth has 500 million square kilometers, so that's 500 million grid points. So that's a computationally very demanding problem. And then only lately it came to looking at AI in detail. So that was actually driven by my sabbatical at Microsoft, where I was part of the team building the infrastructure for chatbots like ChatGPT and whatnot, and also accelerating those greatly. And now the question was, can we combine the two? Can we take the AI knowledge to advance climate sciences or to benefit climate sciences? So, and that's now the new research direction we are engaging in my group. Quite a long story. Absolutely. The main takeaway is that we have a long journey in front of us to make or to enable traditional simulations to utilize all the wonderful benefits that AI is going to give us. And there are so many different ways we can use this. So one way is that AI has opened the floodgates for smaller precision data types, sparsity, and using hardware optimized units such as tensor cores. These units will be available and with everything that it entails in future or even today's architecture. So we now, as climate scientists, for example, we would need to understand how to use those units. Furthermore, we can use artificial intelligence directly to make predictions. As you know, many weather codes today are actually performing equally good or maybe even better in a data-driven AI manner than in a traditional simulation way. So the question is, how can we use this for climate predictions? So climate is long-term weather over the next 30 years, for example. And it's not specific weather like tomorrow, but it's a distribution of potential weather events that we're interested in. And then the last one is, how can we actually take AI to accelerate pieces of these simulations? So for example, radiation schemes. So how does the sunlight interact with the clouds and other things in the atmosphere? And this is also something that is not too well understood, but there is some light at the end of the tunnel that we can actually change those schemes, exchange those schemes to run at a much higher performance and at a reasonable or even sometimes better precision. So these are the three main aspects that I hope the audience will take away from my talk, and also some initial ideas how to do it. So the problem is not solved. I wouldn't be talking about it if it was solved, but it's a very interesting thing to engage in. Absolutely. The opportunities are really to take advantage of the big market. So machine learning is very soon going to be $1 trillion market, which is about which is a big part of the IT industry at whole. So if you're not using these innovations coming from that particular market and aimed at that market, we're just losing out. So really what we have to do is we have to understand how to utilize these accelerators, be it directly via machine learning workloads, or be it indirectly to rewrite our mathematical formulations of simulations or maybe other problems to benefit from the data types and the special pieces that these accelerators get to us. So that's the main opportunity I think we have.